Good afternoon, Prof. We are Team 22. We'll be presenting on the topic image compression by seam carving. Next. So, this is our table of contents. We'll talk about what is seam carving and how it works, the 3 techniques used, and also to showcase the demo and analysis and conclusions. So what is seam carving? Unlike standard scaling and cropping, seam carving is like an intelligent way to remove seams and ultimately resize the image based on low energy and high energy seams. So basically it scales the image without distorting or cropping the image. And then how does seam carving work? So it actually is split into a 3-part process, which is computing of the energy map, where we calculate what are the high and low energy areas, high being the important parts of the image and low being the background image. Next is we'll find the seam. So we'll find from top to bottom what is the lowest cumulative energy, and then after finding the seam we'll remove the seam, the lowest energy seam, and then keep on repeating the process until it's like at the correct size. Next.
So now I'll talk about the 3 techniques we use in our program. So for our program, we have 3 implementations: dynamic programming, greedy, and GraphCut. So I'll go through each of these implementations. So for dynamic programming, what it does is that it finds the globally optimal path. It does so by calculating the cumulative cost for every pixel. This results in a globally minimal path. It is computationally more expensive than the greedy algorithm, but it ensures that the image is cropped correctly. For the greedy algorithm, it uses a local heuristic. It is faster than the dynamic programming method. This is due to the way that it calculates a seam. It does so by checking for the cheapest neighbor. But greedy does not account for globally optimal path. So further down the path, it may encounter a high energy neighbor, but it will still cut through it anyways, because this is the path it has already chosen. So this might result in artifacts. For the last implementation, it's GraphCut. What GraphCut does is that it treats the entire picture with each pixel. It treats each pixel in the entire image as a node in a graph. So for the GraphCut, we have to solve for the max flow min cut problem, and for our specific implementation, we use Dijkstra's. So we traverse through the nodes, and then we find the seams where they have the lowest energy, and we perform the seam cutting there. Next slide.
So for the algorithm time complexity, dynamic programming computes the result of all subproblems, giving a total time complexity of OW times H. So this is the most optimum algorithm, and it's the most reliable and well-balanced one. And as for greedy, it also has the same, OW plus H time complexity. It's a faster algorithm as they make the best local choice at each step. However, they do not explore all possible possibilities, so they may sacrifice global optimality in some cases. And then for the last will be the GraphCut, which will have a time complexity of OW times H log W times H. It comes from repeated priority queue operations. This makes the process significantly longer, so it will be much slower due to the priority queue operations as compared to the other two. Next.
So for the algorithm space complexity, starting with dynamic programming, it requires a full dynamic programming table, which is proportional to the width times height of the image. So it gives a complexity of O width times height. It also requires an energy map, which is another O width times height, and small amount of space is required to store the final SIM, which is OH. Overall, the memory usage is moderate, and it's mainly because of the full DP grid. Next, for the greedy method, it is the most lightweight. It does not store a DP table at all, so it only tracks a single SIM that is currently tracing. The only major structure it needs is the energy map, which is again O width times height. But beyond that, it uses very little extra memory. This makes greedy method extremely space efficient, though of course it sacrifices the optimality. And next is the graph card approach. Using the Dijkstra algorithm, it has the highest memory usage as it needs to represent all graph nodes, which is the O width times height, as well as an energy map, and also the graph's width, edges, widths. Beyond that, the Dijkstra algorithm requires strong storing distance value and parent map, both also proportional to the number of pixels. Altogether, it makes the heaviest approach in terms of space demand. So in summary, the greedy uses the less memory, DP sits in the middle, and GraphCAD requires the most. This trade-off often influences which method is best suited for the specific application and depending on the memory available and the level of accuracy required.
All right, so now I'll go through the demo. So let's talk about the right panel. So on the right panel, the top is our two images that will be cropped, and the bottom one will be the reference. So the right one is the energy map. So now we talk about our left panel. So this is our control panel. So we can load an image. So let's load an image. Then after that, we have our width and height. So this is how much we want to crop. So let's just choose a small number. So after that, following that, we have our algorithms. So the different algorithms you can choose. Following that, we have our buttons. So process instantly doesn't draw anything on the screen, but it still processes the image. So at the end, you will get the image and you will choose you will show the time. Followed by that is the animate steps. So animating steps will be showing step-by-step seam cutting, where it will draw a red seam line. Lastly, it will be run benchmark. So run benchmark will run all three algorithms without any drawing on the screen. So let's just take a look. Let's just take a look at all of them. Yep. So dynamic programming sits somewhere in the middle, time-wise. So greedy algorithm a bit faster, and GraphCAD one of the slowest. So as you can also see, when we cut, we will cut width and height. So how it's doing that is by cutting the width, then rotating the whole image by 90 degrees, then cutting technically the width again. So that then after that, it will rotate back to the original image. So let's just do that'll be nicer. Okay. So yeah, let's move on.
Yep. So to showcase the performance comparison of the three techniques, we've also done some previous testing on our own device. So here we tested the algorithm on a 1920 by 1080 image and resized it down to 960 by 540. So the results clearly highlight the trade-off between speed and quality, with greedy the fastest method, finishing in about 8 seconds. And this makes sense because it only checks the 3 local neighbors at every row, and it doesn't maintain any tables or do any backtracking. So this gives it extremely low memory usage, but the drawback is that the seams are usually of poor quality. Then as for the more optimal one, dynamic programming, this one is more of the middle ground. It takes about 16 seconds, so it's twice as slow as greedy, but it produces far better results. So dynamic programming builds the full energy matrix and then backtracks the optimal seam. So this extra computation allows the image outputted to be a lot more smoother and visually consistent. Then finally, GraphCAD using the Dijkstra's algorithm. By far the slowest. For our release mode, it took more than a minute to finish computing. For a 1080p image, this method builds a graph with over 2 million nodes and then runs a full shortest path computation using a priority queue. So theoretically, it will offer the most optimal results in terms of output, but the runtime makes it very impractical for repeated usage. Next. So what do all these results tell us? It tells us that DP, dynamic programming, ends up being the best balance between both speed and quality. It's fast enough for interactive applications and produces consistently good seams. Then Greedy is useful only when speed is the top priority, but it sacrifices a lot of visual quality. GraphCut gives you high quality, globally optimal seams, but you pay for it with a very slow performance and heavy memory usage. So ultimately, different techniques shine in different areas, but in most real-world seam carving applications, dynamic programming is still the preferred method because it strikes the ideal between the computational efficiency and the visual output. And that concludes the performance comparison for the 3 different techniques that we have. Thank you.